We know from the definition of mole that 1 mole of anything equals 6.022 times 10 to the 23rd of that thing. Therefore, 1 mole of atoms equals 6.022 times 10 to the 23rd atoms. Remember, anytime we have an equality with different units, we can turn it into a conversion factor. We can use Avogadro's number to go between moles of atoms and number of atoms, or moles of molecules and number of molecules. We have two different ways of writing the ratio based on this equality, one with moles on top and one with moles on the bottom. For this type of conversion factor, Avogadro's number always goes next to atoms or molecules, and 1 always goes next to moles, because the relationship is that 1 mole equals Avogadro's number of atoms or molecules. Let's look at an example problem of using Avogadro's number as a conversion factor. We want to find how many calcium atoms are in 30.00 moles of calcium. We would start with the known quantity, 30.00 moles of calcium. Then we would choose a conversion factor with moles of calcium on the bottom to cancel out with the moles of calcium we started with, and atoms of calcium on the top, since we are trying to get atoms of calcium as our final units. Avogadro's number would get filled in next to atoms, and 1 would go next to moles. So that tells us we are multiplying our 30.00 by Avogadro's number, and we come out with 1.807 times 10 to the 25 atoms of calcium. We can also convert in the other direction, from atoms to moles. In this example, we are given 1.00 times 10 to the 20 atoms of calcium and asked to find moles. We would start with the number we are given, 1.00 times 10 to the 20 atoms of calcium. Then we would choose a conversion factor with atoms of calcium on the bottom to cancel out with the atoms of calcium we started with, and moles of calcium on the top, since that is what we are trying to solve for. Avogadro's number goes next to atoms, this time in the denominator of our conversion factor. That means this time we are dividing by Avogadro's number, and we come out with 1.66 times 10 to the minus 4 moles of calcium. If we were to take 1 mole of a particular substance and weigh it, that mass in grams would be the molar mass of that substance. The molar mass of an element can be found by looking at the periodic table. It is the same number as the average atomic mass, it just has different units. The average atomic mass is mass of a single atom in atomic mass units. The molar mass is the mass of 1 mole of atoms of that element, and the units are in grams. This slide shows 1 mole of some different elements. Notice that the masses are different for different elements. However, each weigh paper in the picture has 6.022 times 10 to the 23rd atoms, or in other words, 1 mole of atoms. For example, 1 mole of zinc atoms weighs 65.4 grams. If you look up zinc on the periodic table, you will see 65.4 as its molar mass. We can use molar mass as a conversion factor. Anytime you are going between grams and moles, or vice versa, you will use molar mass as the conversion factor. We use the units of grams per mole for molar masses to make it easier to cancel out our units. In our calculations, the molar mass always goes next to grams, and 1 will go next to mole because molar mass is number of grams that is equal to 1 mole of a substance. Since our units are grams per mole, we could write the conversion factor with grams on top and moles on the bottom, since per means divided by, or we could flip the conversion factor and have grams on the bottom and moles on the top. We will choose the conversion factor that best cancels out the units in our calculation. In this example, we are given 4.7 grams of potassium and asked to turn it into moles of potassium. We will be taking the mass of potassium in grams and dividing by the molar mass of potassium to get moles of potassium atoms. You don't necessarily need to memorize that going from grams to moles is dividing by molar mass. As long as you set up your conversion factors properly with your units and fill in molar mass next to grams, you will know whether to multiply or divide. In this problem, we start with the number we're given, 4.7 grams of potassium. Then we write a conversion factor with grams of potassium on the bottom to cancel out with our starting grams of potassium, and moles on the top since we're trying to solve for moles. We fill in the molar mass of potassium from the periodic table next to grams, and 1 next to moles. Since the molar mass had to be on the bottom to go next to grams, that tells us to divide by the molar mass, and we come out with 0.12 moles of potassium. Notice that the molar mass is different for different elements, so this problem would be different if it were magnesium or iron instead of potassium. We can also go in the other direction, from moles to grams. This time we will be multiplying by the molar mass. We're trying to find the mass of argon that corresponds to 9.2 times 10 to the minus 4 moles of argon. When you hear the word mass, think grams. So we're going from moles of argon to grams of argon. First, we start with the number we're given in the problem, 9.2 times 10 to the minus 4 moles of argon. Then we write a conversion factor which has moles of argon on the bottom to cancel out with the moles of argon that we started with, and grams of argon on the top since we are trying to solve for grams. We fill in the molar mass of argon from the periodic table next to grams and 1 next to moles. That tells us to multiply by the molar mass, and we come out with 0.037 grams of argon. We can combine our two types of calculations with moles together to go from grams to atoms or atoms to grams. We can't do it directly. We have to go through moles using two conversion factors. In our first step, we go from grams of copper to moles of copper by dividing by the molar mass of copper. And in the second step, we go from moles of copper to atoms of copper by multiplying by Avogadro's number. Again, you don't need to memorize whether to multiply or divide, as long as you set up your conversion factors properly. In this example, we're finding how many copper atoms are in 5.00 grams of copper. First, we start with the number we're given in the problem, 5.00 grams of copper. Our first conversion factor needs to have grams of copper on the bottom to cancel out with the grams of copper in our starting number, and moles of copper on top, since that is the intermediate we are trying to get to. We fill in the molar mass of copper next to grams and 1 next to moles. Rather than plugging our numbers into our calculator now, we can add on our second conversion factor and do them all together. Our second conversion factor needs to have moles of copper on the bottom to cancel out with moles in the top of our first conversion factor, and atoms of copper on the top, since that is what we are trying to solve for. We fill in Avogadro's number next to atoms and 1 next to moles. So we are doing 5 divided by 63.55, then multiplied by 6.022 times 10 to the 23rd, and that gives us 4.74 times 10 to the 22nd atoms of copper. How many atoms of magnesium are in 0.546 moles of magnesium? Is it A, 9.17 times 10 to the minus 25 atoms, B, 7.43 times 10 to the minus 23 atoms, C, 8.00 times 10 to the 24 atoms, or D, 3.29 times 10 to the 23 atoms? To do this problem, we need to make sure we're doing the right conversion. We know that we can go between grams and moles using the molar mass, and we can go between moles and atoms or molecules using Avogadro's number. So we need to look at the problem and see which things we're trying to find and which things we're starting with. We have moles and we're trying to find atoms. So we just need this particular part between moles and atoms.
So we're going to use Avogadro's number. And we always start out with a number we're given, 0.546 moles. We're going from moles to atoms. And it's always a good idea to write moles of what, atoms of what, because we're going to get into some more complicated problems later in the semester where the substance might change. So we're going from moles of magnesium to atoms of magnesium, and to do that, our relationship is that there are 6.022 times 10 to the 23rd atoms in each mole. One goes next to moles. Avogadro's number goes next to atoms. So we're going to be multiplying by Avogadro's number, and we come out with 3.288012 times 10 to the 23rd atoms of magnesium. And that is going to give us the answer of D. Make sure that you don't forget that power of 10. Some students accidentally leave it off. Maybe you forgot to put it in your calculator. So make sure that the whole thing is typed in and you can get your correct answer.